My name's Luke Sleeman, and today I'm going to be giving a presentation titled TensorWhat, an introduction to AI on mobile. AI can be an extremely dense subject. It's really very hard to get a grip on. Hell, we don't even really know what to call it. Is it AI, machine learning, deep learning, machine intelligence? My background is as an Android developer. I'm definitely no expert in the field. I'm really just an interested observer. What we're going to do is we're going to cover a lot of broad ground today, but we're not going to go into any area in a lot of detail. Coming out of this presentation today, what I really want you all to understand is three things. Firstly, just what is it? Secondly, when would you want to use it? And thirdly, if you do want to use it, I want you to come away with enough information so that you know what to start Googling for. My presentation will have three main parts. Firstly, I'm going to talk about some key AI technologies. Then, we're going to discuss the TensorFlow library. Lastly, we're going to close up with a demo where I shall use my mobile telephone to recognize a banana. We're going to start today by actually looking back at the past. I hope you can forgive me for this digression, but I wanted to talk about my own personal AI journey and why I am interested in the field. This is a picture of my very first computer, the Panasonic JB3000. It runs DOS version 1 and it uses 8¼ inch floppy disks. I got the computer when I was 8 years old, and it came with two programs, WordStar for word processing and BASIC for programming. Now, as an 8-year-old, I really wasn't that excited by word processing. I wasn't that into it, but I did spend a lot of time using BASIC to learn how to program. The other thing I spent a lot of time doing is reading science fiction. And one of my favourites was this book. It's 2001: A Space Odyssey. Now, I'm not sure how many of my viewers will have read the book or seen the film, but one of the coolest things in it is they have this computer that controls the spaceship called HAL 9000. HAL is what most people think about when they hear the term AI. He's a really good example of what we would call general purpose or strong AI. HAL can reason, that is, use strategy, make judgments under uncertainty, solve puzzles. He can also represent knowledge, including common sense knowledge. He can plan, he can learn, and he can also communicate in natural language. That is, people can speak to him and he talks back. But most importantly, he can integrate all these skills towards common goals. Now, also, HAL 9000 would wanting to kill all humans, but as a kid, I wasn't too concerned about the kill all humans bit because I decided to use my computer to program up HAL. In the basic programming language, of course. Now, in BASIC, it's easy enough to get the user's input, but once you've got something from the user, unfortunately, it turns out that deciding what to do so the computer can react in an intelligent manner is quite a bit trickier. And I failed miserably at it. You might be thinking, ha, what an idiot! An 8-year-old thinks he can write a general purpose AI in BASIC? But it turns out actually, I'm in good company. When electronic computers were first developed 60 years ago, there was a great deal of optimism and research into artificial intelligence. Here are a few quotes from some AI pioneers. Within 10 years, a digital computer will be the world's chess champion. Within 10 years, a digital computer will discover and prove an important new mathematical theorem. From 1958. Within a generation, the problem of creating artificial intelligence will be substantially solved. From 1967. The early AI pioneers thought that AI was going to be something relatively straightforward. Something they could solve with a few grad students and a year or two of research funding. All this early optimism led to a backlash when people started to figure out just how staggeringly difficult creating true AI was. In the 70s, funding for the field collapsed. The entire idea of AI became tainted. We don't even like to use the term AI. We call it machine learning or machine intelligence. Fortunately, the AI winter is now long past. In the previous 10 or 15 years, the field of AI has shown some really great breakthroughs. We've got IBM's chess-playing computer, self-driving cars, AlphaGo by Google beating the world champion at the Go game. And part of this is we've made some really important breakthroughs in terms of designing and training neural nets, along with other AI techniques. But another very important part of this is so much of machine learning is really a data game. We need absolutely huge data sets and the computer power to be able to process them. We're just now reaching the stage where we have enough information and enough CPU power to be able to do interesting things. All these breakthroughs are really important, but I believe it's in mobile where AI can have the greatest impact. All those things on the previous slide, like self-driving cars and beating the world's chess champion, they're really hard things. They're tricky to do. But on mobile, adding just a little bit of smarts can go a long way. One example of this is smartwatches. Personally, I'm a very heavy user of my Android Wear watch, and one thing I use it for is when I'm cooking. I'll just talk to it and say, like, okay, Google, convert 2 cups to litres, or convert a pound to grams. Now, this kind of stuff, the voice recognition, parsing the sentence, figuring out some unit conversions, compared to like a self-driving car, that's not enormously difficult AI. But because it's always there, always with me on my watch, it can make an enormous difference in people's lives. Really, one of the first reasons why AI on mobile is important is on mobile you have very limited input compared to desktop. You've got these tiny screens and you're sort of jabbing at them with your fingers. But also, we have a wide variety of sensors in mobile devices. Motion, audio, compass, GPS, camera. Coupled with that, mobile apps also have very short interaction times. The users will spend just a few minutes using their phone doing something with it, and seconds to interact with their smartwatch. Compared to, if you imagine your desktop computer, you'd probably sit down to work at a desktop for maybe hours at a time. This constrained input and limited interaction means intelligence is very important, and just a little bit in mobile can go a very long way. Now let's have a look at some key AI technologies. And by key AI technologies, I really mean neural networks. There are lots of other interesting things going on, but neural networks are responsible for a lot of the important technology we're going to be looking at today. To explain neural networks, we're going to start with a classifying problem. Here we've got a data set which has 2 dimensions to it. We'll call them x1 and x2. And it doesn't really matter what this data is, but perhaps what we're looking at here is customers for our website. And x1 is how often they visit the website, and x2 is how long they spend using it. And because we've just got 2 dimensions to our data set, we can helpfully draw it on a graph. And you can see there that it easily separates out into 2 groups. And it's super easy to write some code to classify that data, to divide it in 2. Basically, we just write an if statement, and there, we've chopped it in half. We've drawn a line through it. And what we've got here is a very primitive classifier. However, it turns out that classifying things is a very common problem. So let's make our code a little bit more reusable. Let's do some refactoring. Firstly, that hard-coded 0 is bad, so let's introduce another variable, b, our bias. And by adjusting this b, we can move our line around a little bit. And to make things more reusable, let's introduce some weights on our x1 and x2 parameters. This allows us to adjust the angle of the line so that we've got a different data set where we can fit it a bit better. Lastly, this kind of like we're in and we're out stuff is really a bit hand wavy. So let's make the function return the probability that we are in the top data set. So if it's above that line, then we return 1, 100% sure we're there, and otherwise we'll return 0. And what we've actually gone and done is we've created a perceptron or a neuron. These are the basis of neural networks. We have inputs, in this case 2 of them. The inputs have a weight. There's some sort of activation function which works off the sum of the inputs, and in our case we were just returning 1 or 0. It's what's called a unit step type of activation function. There are other ones like tan or something called ReLU. These perceptrons are really powerful things. In particular, because the computer can automatically adjust all the weights to learn to fit a dataset by itself. We don't need to program in the W1, the W2, the B. We can figure them out by itself. So, let's do a demo. Now, what we have here, you can see, is a website called the TensorFlow Playground, and it's really great for mucking around with neural networks. And you can see here over on our right, we've got our data, and here in the middle, we have our neural network, and here we have our inputs, x1 and x2, leading into it. And when I click the play button, something really interesting is going to happen. The computer automatically learns to adjust the x1 and the x2 weights to build build a classifier to divide our data set in 2. And we could like throw a completely different data set at it and run it again, and it will learn to come up with some values that will reflect that data set and map that data set. Now, what happens if we have something a little bit more complex than just, these 2 easy groups? For example, this circle. Well, it turns out that no matter how long we leave the program here learning and trying to automatically adjust its weights and fiddle the numbers so we can fit that data set, it's actually never going to happen. We're just not going to be able to do that with one perceptron. But if we add 3, and then run it, something very interesting happens. What's going on is just with 3, we've been able to actually quite nicely match that data set. And we can find out how it's working by hovering over each of the neurons. The first one's sort of dividing the top and the bottom half. The next one's dividing, sort of the bottom left corner, the top right corner. And the last one there is dividing left and right. And when all of those outputs get summed together, we've got this kind of wonky triangle thing that actually divides our data set quite well. And, if we add more neurons in, we're able to get like a much nicer fit. So rather than having a wonky triangle, we're now going to have like a much nicer, smoother circle. And you can see what's happening there is they're dividing the area up much more evenly. All right, what about an even more complicated data set? We've got a swirl. Well, again, even though we have a lot of neurons there in the first layer of our network, we're still, no matter how long we're going to let this run, we're still not going to be able to find a good match for it and find a good fit for it. So how are we going to match this data set? Well, it turns out, firstly, we've got to tweak the activation function. But secondly, if we add some more layers, we're going to actually be able to build something that will match this data set. Now, because we have so many layers here, it's going to take an actual fair amount of time to run. The computer's got to do some fairly complicated calculations, and you can see there's lots of interlinkages and lots of interrelationships between the different layers and neurons. But while it does its maths and while it does its learning, let's have a quick look at what's going on. Again, you can see here in the left, in the first layer, it's just basically dividing up the area into top and bottom section, left and right, just doing some simple like chopping the plane in half. But then what happens in the middle layer is it uses the outputs of the first layer to build more complex shapes. For example, this thing, and this thing, and this thing. And then what's going on in the final layer is it's combining those intermediate shapes to something even more advanced and complicated. And then when all they get added together, you can see again, we've managed to build up a fairly good fit for this complex data set. What have we learned about neural networks? Firstly, they learn to recognize patterns from our training data, and they can work for very complicated patterns. But also, they can take a long time to train, and you really have to choose the right, what are called hyperparameters. That means the right number of nodes, how they're laid out in the network, the activation function, input transformation, and so on. If you make the wrong choice in how your network's structured, then it doesn't matter how long you train it for, it may never be able to fit your input data. Now let's look at some of the more advanced things that have been built using neural networks. Because the idea of neural networks is very simple. But it turns out if you structure them in different ways, they're good for many different things. And we're going to start by looking at image search. Last year, Google rebranded their photo product to Google Photos. And one thing that's consistently amazed me about Google Photos was the search. It's able to search and organize your photos without any kind of tagging or associated data. It actually can understand what's in your images. And these are from my private photos that I've taken. They're not like out there on the web somewhere with text describing them. This is just things I've photographed with my phone. On the left here, you can see my boat, Bumblebee. And it's able to read the writing and recognize the logo. In the middle there, you can see it understands the photos of my kids and what they're doing, rock climbing. And one of my favorite features, it even has emoji search. So you can see there that it's pretty small and hard to see, but I've searched for the smiley face with sunglasses emoji, and there we go in the results. It's shown pictures of smiling faces with sunglasses. And this kind of intelligence, this sort of stuff is particularly important on mobile. On my desktop computer, I've got a lot of photos. I've got like 30 or 40,000 that I've taken with my DSLR, but I've got them all processed and organized into folders and backed up on portable drives. And what I'll find myself doing on my desktop is I'll sit down for like 2 or 3 hours to like sort through and organize my photos. But on mobile, I find myself wanting to really quickly get random access to photos of a particular thing. So for example, I'll be talking to somebody about my boat and they've sort of got no idea what this thing is, so I'll quickly like search and bring up that photo. Or I could be talking to my mum about what we did last weekend and I want to bring up those rock climbing photos. Let's have a look at how image search works. One approach that has had a lot of success in image recognition is deep belief networks. And we've already seen a very basic deep belief network doing image recognition with that swirl pattern I showed you before. A deep belief network consists of a number of layers that are stacked one after another. Each layer recognizes simple features, and the later ones recognize more complex structures. So this is a visualization of what each layer in a facial recognition deep belief network is doing. The early layer recognizes basic features. We've got things like gradients and edges. The deeper layer combines those features into more complex objects. And then you can see at the end all of these faces. And what's really interesting is that none of the faces in the last image are actual real people. They're just what the network has learned the concept of a face is. Deep belief networks are also a type of autoencoder. And this means they can learn by themselves. So for example, with our facial recognition, it doesn't need to know the names of the people it's recognizing. You could just feed into the network a bunch of pictures of your friends and it will learn to recognize them and tell them apart. And it's only at the final stage we'll do some what's called supervised learning and teach it the names of the people that go with the faces it's learned to recognize. Speech recognition is another technology that's super important on mobile, and not just on phones, but particularly on smartwatches. Having good speech recognition enables whole new categories of Internet of Things devices. For example, the Amazon Echo just wouldn't exist without solid speech recognition. Personally, I make really heavy use of the voice recognition on my watch. And about a year ago, it suddenly went from basically useless to really, really good. And the reason it improved so much so quickly is Google started using something called recurrent neural networks to do their speech recognition. Everything we've seen up to now is what's called a feed-forward network. That means that basically you put one set of inputs in and it works its way through the layers and then we get one output out the back. In recurrent neural networks, that output is fed back in as input, like a loop. And this actually provides a type of short-term memory. It also allows recurrent neural networks, RNNs, to work with a stream of input and provide a sequence of results over time. And not only is this good for speech recognition, but really any sort of signal over time, like forecasting or predicting control inputs. Lastly, we're going to look at OK Google, Siri, and, it's a mouthful, recursive neural tensor networks, RNTNs. OK Google and Siri are completely changing the way we interact with devices. We're moving away from an app-based model of tapping buttons and icons towards an interaction model where we're having a conversation with our phone. This works well for those quick, short interactions people have with their mobiles. Now, obviously, Siri or OK Google is an extremely complex thing. There are lots of different bits, the speech recognition, the search engine, all kinds of data mashups and intent recognition and so on. But one of the most important parts of conversational agents is figuring out what the user is actually asking, natural language processing and sentence parsing. Basically, we need to be able to extract out the nouns and verbs from a sentence and figure out how they all relate to each other. We need to be able to build a parse tree of our sentence. It turns out, for example, that in English there are many ways that this sentence can be understood. Alice drove down the street in her car. Does it, for example, mean that Alice was driving down a street inside her car? What is it that's in the car? Is it Alice or the street? Well, as human beings, we know that it probably isn't a street that's inside the car. But how would a computer figure that out? RNTNs are very good for sentence parsing and anything that involves hierarchical data. An RNTN has a tree-like structure. So basically we have a root node and a left and a right node. And just like recurrent neural networks, the complexity in RNTNs is not so much how they're structured, but how they're invoked and the data flows through them. RNTNs are invoked recursively, feeding the output from each previous step back into the network. At step 1, we feed the first parts of the sentence into the first two leaf nodes. And then the root node will output two values, a class and a score. The class is a representation of the current parse tree, and the score is how likely that parse tree is. At the next step, we feed the output back into the left node, and the next word in our sentence gets fed into the right. And this goes on until all the values have been fed in, and we have our final output, which is a parse tree, and how likely that parse tree is. In something like Google Now or Siri, obviously what's going on would actually be a lot more complex. To parse English, a RNTN actually needs to evaluate all the possible sentence structures and parse trees and determine which one is the most likely. So what we've got here is really a very simplified example to show the main idea behind an RNTN, that recursion can be used to represent a tree structure. RNTNs can be used to understand anything with a hierarchy. We're going to step aside from the different kinds of neural networks and have a look at TensorFlow. TensorFlow is a library for implementing various AI techniques. When you dig into it though, actually it turns out there's really nothing AI specific about it. Mostly it's just a bunch of things for doing very tricky maths. It's all based on creating data flow graphs. Basically what you do with TensorFlow is you create a model, which is a network of nodes. Each node takes in as input a multi-dimensional array called a tensor, processes it, and then puts out another tensor as its output. And the tensors flow between the nodes, hence the name. It turns out that this is a really great way to build computations which are portable, parallelizable, and can run on, for example, a GPU or an embedded mobile device or in the cloud. And there's also lots of existing models that have been built using TensorFlow. We're going to look at some soon. Very quickly, here's what some very basic code looks like. It's written in Python, but there are other language bindings for TensorFlow, including C++. And essentially what you do is you define a node, in this case just a constant. We build a session and we pass our node into the session, telling it to run across that node. And session's going to evaluate it, all of the nodes we've put in, pass the data between them, and we get output. In this case, hello TensorFlow. A slightly more complicated example, here we're defining two nodes, again, both constants. We're adding them together, passing them into the session, and when the session runs across them, we get 42 as the output. It turns out that if you want to build an app with really great AI in it, the simplest approach is not to use TensorFlow at all. Actually, it turns out this stuff is really hard. Fortunately, there are loads of great cloud services available, and they're super easy to use. Basically, you just send in some JSON with your input. It'll run on their server, and you'll get some JSON results back. And the great thing about this is we don't need to worry about how all these things work. So Google has various AI things they do exposed as APIs anybody can use. We've got the Cloud Vision, the Cloud Natural Language for like natural language processing, Cloud Speech for speech recognition. And as Google improves these things and makes them better, we're going to get those updates for free. We don't need to be experts in AI to get all of the improvements and benefits of the research that's occurring in that field. Amazon's also got an entry in this area. You can send it data sets and it'll learn how to fit them, a bit like that demo I did a bit earlier. And one very interesting startup, there's one called Algorithmia. It's an algorithm marketplace. So if you're looking for an algorithm to do a particular thing, say, I don't know, read the text off a business card and parse it, there'll be a bunch of them that people have invented that are they're hosted on the cloud, and you can purchase them and make use of them in a hosted environment. If you want to do something a little bit more complex than what the cloud services provide, you can also run TensorFlow on the server side. And there's a few options for how you can serve up TensorFlow models. One really quick and easy, but also pretty hacky way is just to run a shell script and pipe in some input and parse the standard output. What we've got going on here in the code example is we're passing some text into a syntax net, which is a model for doing sentence parsing, and we're getting the parse tree of the sentence there as output. And actually, a person that attends the Google developer group that I went to managed to use a very similar approach to this to build a really cool AI demo just over the weekend that basically took input sentences as input, did some really cool things, displayed the result in a mobile app. So it's a bit hacky, a bit ugly, but it's very quick and easy to build an API around something like this. Another approach to talking to TensorFlow on the server is something called gRPC. gRPC is Google's remote procedure call library. Essentially, with gRPC, what you do is you define the methods that your server wants to expose in a special file called a .proto file. And then you can run a generator and produce various language bindings to call those methods that your server is exposing over like HTTP, TCP, or so on. Actually, when I looked at it, it's all kind of complicated, especially for somebody that's used to, as a mobile developer, just having really nice, clean, straightforward JSON APIs. But TensorFlow does have built-in support for exporting models via gRPC. One of the great things, though, about TensorFlow is that it's portable. You can also run it on a mobile phone directly. Essentially, what you do is you'd use the TensorFlow C++ library with the Android NDK, or on iOS you can just include C++ libraries directly via Xcode, and you would load up a pre-built and pre-trained model and feed the data into it. Now, when I actually started playing around with this myself, it turned out to be all kind of complicated, actually. We needed to use a special build system that is used for TensorFlow called Bazel, which is different to the standard build system we used for Android apps. And really, it's just a huge, nasty mix of like C and C++ and Python and Java and this thing called Swig. And they've all got their various build systems and environment variables and package managers that you need to set up. It's pretty nasty stuff. Fortunately, Google have said that changes are coming. This October and November of 2016, Google says that they're doing a big refactoring and cleanup to make all the everything use a common C API for TensorFlow, and it will then be very easy to build like language bindings that talk to the C side. So fortunately, things are going to get better soon. It's all well and good to be able to run TensorFlow, but what about our model? Where do we get our neural network from? Well, one option is to use TensorFlow to build your own. But we're going to need a few things. Firstly, a large data set, and really, that should say enormous. There's an academic data set called MINST, which consists of images of handwritten numbers, and it's often used in papers. People train up neural networks and various techniques to recognize numbers and tell them apart. And that has 50,000 images in it. Another academic data set called ImageNet. It's used for like a lot of people do research training up image recognition networks, and that has 500 terabyte of thumbnails. Just tiny, like 200 by 200 pixel thumbnails. It's got like 500 gigabytes of them. You're also going to need a huge computer. When I was looking at the documentation on some of the TensorFlow models that had been published on the web, and I was sort of reading through the README, and the people that published it are saying, this network's like really great. It's you can train it really quickly and easily, and you don't need a lot of resources. It's so lightweight that you can train it on only one computer with only 8 Tesla K40 GPUs. And I never heard of a Tesla K40, so I Googled it. It turns out they're more than $4,000 each. And they were saying, we trained it on a computer that only had 40 gigabytes of memory, and so on. You're also going to need a lot of time. Weeks, months can go into training these things. And then, because it's all so complex, we've got this enormous computer, we've got this huge data set we're gathering, we're spending weeks or months on training runs, probably you're going to want a team of PhDs to organize and run all of this stuff for you. Because if you stuff up your neural network and design it badly, then you're going to waste an awful lot of time and an awful lot of money. Now, I don't want to put you off playing with AI, because individual people have achieved some really cool things, really fun stuff. But doing Google level image recognition isn't something you're going to hack out in a weekend. It's something you will have to take seriously and really dedicate resources to. Fortunately, we are at the stage where this stuff is at least feasible. A $32,000 computer might not quite be hobbyist level, but a lot of my customers would spend at least that much getting a mobile app built. If building a new model is too hard, what about using somebody else's? One already built and trained by our team of PhDs. Actually, there are loads of really interesting TensorFlow models that Google has published to GitHub. There's one called SyntaxNet, which is a generic model for parsing text. That would be, French or Chinese or English. And built on top of that, we have a parser called Parsy McParsface, which is used to recognize English and extract the structure out of it. There's also a model called TextSum, where you can feed it in part of an article and it will produce a summarization of that article. One really cool one that I saw, I was extremely impressed by the demos, was called Show and Tell. It's an image caption generator. So you feed it in a photo and its output will be some text that says, "This is a man on a surfboard catching a wave." Or, "This is two girls in a sand pit playing with some toy cars." Lastly, we have another model called Inception, which does image recognition. It's been trained up with the ImageNet academic dataset, and there are a list of 1,000 different objects it can recognize. And it's actually really good at this. In its top 5 guesses, it gets about 5.6% error, which is really not bad. It represents a load of research, and it's just sitting there on GitHub. This leads us very nicely into our demo. We have our model, the Inception model, which is already trained to recognize 1,000 objects, including all kinds of different fruit. We have TensorFlow, which allows us to run models on various devices, including our mobile phone. So let's tie them all together and use our phone to recognize a banana. Firstly, I want to be 100% clear, this isn't something I've developed. It's a pre-existing demo app in the TensorFlow GitHub repository. Here's an overview of what the app is doing. We've got a screenshot of it there on our left, and basically it shows the camera input and outputs the guesses for what it's looking at. And the way that works is we have some Android code, which is used to drive the camera to take the images, and that feeds them into the C++ code, which is using the TensorFlow library to load and evaluate the Inception model. The C++ code, after it's run the model, returns out the classifications and their confidence scores, and they're shown in the Android app UI. So, without further ado, let's move over to our demo. Here we have my mobile phone, and I'll just start up the TensorFlow demo app. And you can see what's happening is you can see a lovely view of inside my office coming through the camera there. And here on the table, we have a banana. And if we point the phone at that, what does it say? It's about 60% sure that 70% sure that we're looking at a banana. That's great, okay? What about an apple? A hip? A pomegranate? Not quite. That's Granny Smith at about 30% probability. What about an orange? Oh, it's great at recognizing oranges. Here we've got a few other things as well. Here's a rope with knots in it, and it's really good at recognizing knots. It's definite that that's what it's looking at. And here's a clock. Let's see, a stopwatch, an analog clock. That's a pretty reasonable guess. Let's wave it round, see what else we can recognize. Here's a Inception. Thinks that's a cash machine, not quite. A notebook computer with a keyboard. That's actually pretty good. Spacebar. All right, I'll shut down the demo now and move back to the presentation. We've seen some really amazing breakthroughs in AI. The real-time image recognition we had on the telephone was something I never thought I would see happen in my lifetime. When I first saw this run, it floored me. And I wanted to bring things full circle and see how the technology today stacks up against our definition of a strong or hard AI. Are we any closer to strong AI? Well, firstly, can we reason? Can we solve puzzles? Make judgments under uncertainty? Well, yeah, actually, we do have a decent amount of experience doing that. We've got lots of puzzle-solving things like the chess-playing AIs and AlphaGo, and neural networks are great at dealing with uncertainty. That's what they're really good at. Okay, what about representing knowledge? Well, no, not at all. It's not something we really know how to do, particularly common sense knowledge. Computers are still awful at common sense. Can we plan? Well, sort of. There are custom algorithms for doing things like route planning and things like forecasting, but it doesn't really seem to be a generally solved problem. What about learning? Yes, that's what neural networks are all about, learning from their input data. They're fantastic at that. Okay, can we communicate in natural language? Well, yeah, we're pretty good at that as well now and getting better all the time. Okay, Google, Siri, conversational agents, and bots. There's been a lot of research and work done in them, and they're continuing to get better. Lastly, can we integrate all of these skills towards common goals? Well, no. We have got absolutely no idea how to do that, which is not surprising since we do have a bunch of things earlier in that list that are also not ticked off. Lastly, what about this kill all humans stuff? Well, it makes for great books and fun movies, but I don't really think that's going to happen. While the thing is though, while we're not going to have an AI built with the goal of killing all humans, that doesn't mean we're going to have an AI which will work for the betterment of all mankind. It's entirely possible. You could imagine, like 15 years down the line, we have got a few more AI breakthroughs, maybe some more things in this list have been ticked off, and suddenly Google has an AI with the goal of maximizing the value of Google shares, which is great for Google shareholders, but perhaps not so much for the rest of us. I think thinking and worrying that we're going to be wiped out by AI is a bit far-fetched, but thinking that AI is going to benefit some of us and not all of us is entirely plausible. We can't just leave this stuff in the hands of the big four tech companies. Google has taken great steps with releasing their code and releasing their research, but we as developers need to build on that, to understand it, to use it in our own software, and to democratize AI. AI needs to be for everyone. And it needs to be especially for mobile. We've seen how AI is particularly useful on mobile. We've seen how there are many useful things you can do today with very little effort. I want everyone to start thinking about how we can use these techniques to bring value to our users. And I want you all to use what you've learned to go out and build great things. If there are any questions, please leave a comment on the YouTube video and I'll try and get back to answer them. Thank you, everybody.